How long do you spend on your phone, tablet or computer? Well, imagine there's over 300 million terabytes of data created every day. That's the equivalent of every person watching videos non-stop for over a month in America. If you can imagine how much data goes over the internet, how does it not crash into each other or cause big traffic jams of data? The answer to that is the use of clever algorithms. Prim's algorithm is used to form a minimum spanning tree for multicasting. So what does this mean? Well, let's explain multicasting first, then the Prim's algorithm using two examples. And stay for the second half of the video if you'd like to see these examples work in Python code. Data is sent from router to router over the internet, so you can think of these as nodes in a network. You can see here we can construct the spanning tree and then pass messages along the path given in that tree. That way, when we pass messages, then the message only goes once to each node. We want to do that efficiently, and this is where we use an algorithm to find the minimum spanning tree. Here's a network we've used in previous videos. It represents the routers and the connections to the routers, and it also has costs. So we can represent the network here with these numbers as routers or nodes in the network. We start at 1 and we want to visit each node with the minimal cost to get the minimal spanning tree. So let's start off at 1. We can see the smallest cost is the cost of 1 goes to node 3. Now node 3 we can see other links, other connections to other nodes, and 2 is the next lowest cost, and we can get the connections from that node, node 2, and also cost of 2 we can get to node 5. So now we've got a connection from nodes 1 to 2 to 3 to 5. All we need now is connections to node 4 and node 6. Smallest cost to node 4 we can see another cost of 1, so a total cost of 3 from our start. We complete our network and we can see the minimum cost from node 5 to 6 is 2. So here is our minimum spanning tree. We can visit every node with the smallest cost, and we completed this minimum spanning tree by starting at node 1. You don't have to start at any specific node, but you want to finish with the minimum spanning tree. Let's have a look at the code. So we've used the adjacency matrix in previous videos, and here's just a reminder. Essentially we just have the nodes and then we use a table with the values, the costs of each node. So in this example you can see node 1, we can go to node 2 for a cost of 3, to node 3 with a cost of 4, and node 4 for a cost of 2. You can put that in the adjacency matrix. We put that into code in Python. You can see we put it into the graph, and for each number you can see the list of costs. And here is our code with the graph class, where we have the initialization, the printing method, and also to find the smallest key value. And here is the algorithm. Well, we haven't taught this for a while, so we couldn't use our own code, so we thought we'd change some online code to match our graphs. So here's the code we took from Geeks. You can scroll down and you can see the Python 3 code which we've amended to use in our video, but that's where the code comes from, to give it credit from the author. You can see the code in the editor. We start off with the graph that we've shown you already of our network, and we call the algorithm the Prim's algorithm, and also in the code we have some methods in the class graph. So let's run this and see. We have our minimum spanning tree with the edges from which nodes and the weight. So that's our first example. In the editor we can have a look at the code. Let's start from the top. This is Prim's minimum spanning tree algorithm, and we can scroll down till we see that we've called the algorithm after we've defined the graph. Here's a second example. Again, a network we've used before. We have nodes and costs. We'll start on the left hand side at 1 again. So minimum spanning tree, we can start off, smallest value is 2. We go to node 5, 3, node 2, 3 again to node 7. Here we could either go to node 3 via node 1 or node 5, either 2 and 2 or 4. So probably we're going to use the first one here because we started at node 1. But if you started at any other node, you'd probably go from node 5. So we go 4 and node to node 4. And again, from node 7, we have a choice. So we can choose to go to node 8 with a cost of 2. Then node 10, a cost of 2 again. And also we complete our nodes. We go to node 6 and node 9 from node 10. So essentially this is the spanning tree we get if we start from node 1. You can see that maybe is an idea to try different start points, because our connection from node 5 to node 3 would be better with the cost of 2 rather than 4 from node 1 to 3. So that would be a better spanning tree because it has a minimum or smaller cost. Okay, so here's our minimum spanning tree for our second example. So here we've got a larger graph that we've seen. We've shown the example and our minimum spanning tree. It's exactly the same code as the first example. So let's run this and you can see again this is our spanning tree with the edges from which node to which and the weight. So that's our code in the editor. There is a great new opportunity for anyone interested in learning about Python or any other areas of computing. In the next year, new courses will be added to the Alps Academy, and they will be available to you for free. Written by university professors, they will be specifically designed for international students, which means they'll be easy to understand using simple language. They will even be helped to improve your English if you're interested. How can this help you? Well, leave a comment. Any suggestions you make could be turned into a course. Motivated learners deserve equal access to opportunities. Help us to help you. If you like that video, please give us a like, and if you haven't already, please subscribe.